In this lesson, we'll look at a couple of examples using exponential growth and decay. Starting with example 1, it says, prehistoric paintings were found in a cave in France, and the paintings contain 29% of the original carbon-14. We want to use this equation to estimate the age of the paintings. So first of all, the equation itself we should discuss. Here, t is time. It's an exponential equation because we have e to, it's a negative exponent, so I know it's a decreasing exponential function. Here, this number, negative 0.000121, that is a decay constant, which I'll just label k. And because of the way this number is defined, time is going to be estimated in years. Also, we have a sub 0, or a naught. This is the initial amount of carbon-14. We don't have units on this, but it's probably something like grams or something like that. And then A is the amount of carbon-14 after t years. Okay, so that is like if you put in 5 for t, you're saying after 5 years, what's the amount of carbon-14 that remains? So for this problem, we want to solve for t, time, given that there's only 29% of the original carbon-14 remaining, and a sub 0 is the original amount of carbon-14, and we're not told how much of that there actually is. But there is a way that you can express this. If a sub 0 is the original amount of carbon-14, if you multiply it by 0.29, you're taking 29% of it. So this expression represents the amount of carbon-14 that is remaining in the painting. This will allow us to solve for t, given this condition here. Essentially what we'll do is we'll put this thing in place of a and solve the equation for t. Let's try it. All right, so that's 0.29 a sub 0. That's equal to a sub 0 times e to the negative 0.000121 t. One nice thing we can do at the start here is cancel a sub 0 from both sides of the equation. It's got to be some positive number, so I'm just going to remove it from the equation altogether. And that leaves us with 0.29 is equal to e to the negative 0.000121 t. Second step is, well, I have an exponential equation. I don't want the variable in the exponent, so I'm going to use a logarithm to remove this from the exponent. You can use any logarithm you want. However, I think using the natural log is the best way to go. And the reason for this is the natural log of this side is just a number that you can get from a calculator. But if you take the natural log of e to this entire power, this whole side is just the exponent because the natural log and e are the same base. This equation becomes the natural log of 0.29 is equal to negative 0.000121 t. Again, this natural log and this e cancel, and it leaves us with this. To solve for t, I can divide both sides by this number. On the right, they completely cancel, and it leaves us with t. And on the left, we have the natural log of 0.29, that's a 29, divided by negative 0.000121. Now, not a very useful number. I'm going to put that into my calculator and see what it approximately equals. So it's the natural log of 0.29 divided by negative 0.000121. And, I think I'm just going to round to the nearest integer. I get 10,230, and that's years. So this number here is an estimate of the age of these paintings if we assume an exponential decay by using this formula here. In example 1, we looked at exponential decay. This one is going to be exponential growth. It says the population of a certain country in 2004 is 31.2 million. It is projected that the population will grow to 42.6 million by 2029. So what's the growth rate here? Which means solve for the value, this constant k. Do we have enough information in this problem to do that? Well, let's try to label things in the original equation. Like, first of all, here we have 31.2 million at the start. This is the value of a sub 0. A sub 0 represents our initial amount. I'm going to put it as 31.2, and here we're talking about millions. We also are given this number 42.6 million. Now, what would this represent? Well, this is the value of A when t is equal to what? After some amount of time t, we will reach this population. So we have to solve for what that is equal to. How many years have passed from 2004 to 2029? And that's a total of 25 years. So here, I just took the difference of 2029 and 2004. We now have what we need to solve for k. I'm going to enter in all this information here. So in place of a, I'm going to put 42.6. In place of a naught, or a sub 0, that's 31.2. And then we have e to the, well, k is the thing that we're solving for, and t is equal to 25. All right, let's solve this thing for k. What I'm going to do is divide both sides by 31.2. So 42.6 divided by 31.2. I get a decimal that goes on forever, so I'm going to actually just leave it as a fraction. Here I know they cancel, so on my left side, I'm just going to put 42.6 divided by 31.2. And that's equal to e to the, well, that's really 25 times k. I like putting the thing I'm solving for second. Okay, if you want to remove the variable that we're solving for from the exponent, we're going to take the natural log of both sides. I'm choosing the natural log because it'll cancel nicely with a base of e. In fact, the natural log of e to anything is just this thing, 25k. And on the other side is a mess, but it's the natural log of 42.6 divided by 31.2. To solve for k, I'm going to divide both sides by 25. I have k by itself. K is equal to, as an exact number, that's the natural log of 42.6 divided by 31.2, and then that whole thing is divided by 25. This is something that we can put into a calculator, and then we'll round it as is appropriate. So let's see. The natural log of 42.6 divided by 31.2. Okay, I'm going to take that number and divide it by 25. I think I'll round to maybe 5 decimal places. That's 0.0124, and then here I'll put a 6. So it's not exact, but this is a very good approximate value for the growth rate k. One thing to point out is that here k is greater than 0, and that represents growth in this type of equation where we have e to a number. In example 1, k was negative, it was less than 0, and that was decay.